Hi, welcome back to compression part 2. So a few things just to recap. So compression is the name given to algorithms which reduce file sizes. And last lesson we spoke about compression being the process where compressed data is restored to its original format. There's two types of compression, lossy and lossless. Last video we looked at lossy compression and we began the first part of lossless when we looked at run length encoding. So if you remember, lossy compression is used for images, sound and video, and lossless compression can be used for them, but is also used for text. So with lossless compression, there's two types. Remember, we did run length encoding, and then there's Huffman encoding. And today our focus is going to be on Huffman encoding. So why use Huffman? So a Huffman encoding tree allows us to compress data, allows us to compress the message of the text, whilst keeping all of the data needed to be able to recreate it. So what are the expectations? First of all, we need to be able to interpret Huffman trees. We need to be able to calculate the number of bits required to store a piece of data compressed using Huffman. We need to be able to calculate the number of bits required to store a piece of data using ASCII. And we need to be able to calculate the number of bits saved by working out the difference. You do not need to know how to create a Huffman tree from scratch. So how do we interpret Huffman trees? Well, here we have a sentence. It's a happy hippo hopped. And we can see that there's 20 characters, including spaces. And we need to include spaces because a space has an ASCII value. So we're going to do what's called a frequency analysis. And what we do here is we have a look at how many times each letter appears. So you can see I've got the letter A here, and that appeared twice. I then had a space. And then I counted how many more spaces there were. So there's 1, 2, 3 spaces. I then went to H, and there's 3 of them. 1 on happy, 1 on hippo, and 1 on hopped. And I've done that for the rest of them going down. So there's 20 characters in total, and we can see how many times each one of those occurs. P occurring 6 times has the highest frequency. So we're going to be using what's called a binary tree. Now you don't need to know an awful lot about these, you'll learn a lot more about these at A level, but a quick breakdown of a binary tree is you've got what's called a node, which will be any one of these blue circles with a character in is a node, and this node can either have 0, 1 or 2 nodes attached to it, and they're called child nodes. So you can see this A here has got 2 child nodes, it's got B and C. C has got 2 child nodes, that's got D and E, and E has got 2 child nodes, F and G. And we can see that there's only 2 options, and that's why it's called a binary tree, because binary's got 2 options. So let's have a look at what a Huffman tree actually looks like. So we've got one here, and you can see that on this tree itself are all the characters. And we can see above that sort of how many times each time that character occurs. So you can see A and O occur twice, and we can see P occurs 6 times. And what you'll notice is that the most popular characters are higher up the tree, and the characters that are least popular are near the bottom of the tree. So it takes longer in order to get one of these characters than it does to get access to one of these characters. So this is the anatomy of a Huffman tree. How do we begin to interpret one? Well, one of the things that we need to do is we need to follow the path. So on a Huffman tree, 0 is given to the left and 1 is given to the right. And you'll see every branch, if it's on the left, has a 0, if it's on the right, it has a 1. And what we do is, in order to get the letter A, you can see we follow it down 0, 0, 0, and we end up at the letter A. So what would we do to get to space? Again, we do the same thing. We'd follow it down. We'd go 1, 1, 0, and that gets us to the space. H then becomes 1, 1, 1. What do you think P would be? So P is here. How do we get to P? We follow the path, and that should become 1, 0. And the final one then, let's have a look at y. Y is down the bottom of this tree, so it's a bit further for us to go. Here we go from 0, 1, 0, 0. If we follow that path, we'd get to y. So that's how we can interpret a Huffman tree in order to be able to get the binary value for a character. But what if the binary value was given to us and we need to figure out what character it is? How can we decode a Huffman tree? Well, again, we'd look at the number, so 0, 1, 0, 1. So we know that we're going to go left, right, left, right. And if we follow that, we go left, right, left, right. That brings us out at I. Again, we start at the top of the next one. That goes 0, 0, 1. So left, left, right. And if we go left, left, right, we end up at O. For the next one there, it goes 0, 1, 1, 0. So left, right, right, left. Left, right, right, left brings us at E. And the final one then, 0, 1, 1, 1 is left, right, right, right. And that brings us out at D. So that's how we're able to interpret a Huffman tree. Next bit, we're going to be having a look at how to calculate the number of bits required to store a piece of compressed data, how to be able to calculate the number of bits required to store a piece of data using ASCII, and how to calculate the number of bits saved. So in order to calculate the number of bits used in order to store this text in Huffman, first of all, down the left hand side here, we have all the characters that we had. And we've got the binary values that we figured out in the Huffman tree. One of the things we need to do now is to look at how many bits each character takes up. So we can see A takes up 3 bits, 0, 0, 0, there's 3 bits to represent A. A space is 1, 1, 0, that takes up 3 bits. H is 1, 1, 1, again there's 3 bits. And in total then there's 30 bits for this. But that is only if we had one instance of each of these. But if you remember, we had multiple instances. So there's 2 A's, for example. So there's an A here, and there's an A here. And if you remember, we have 3 spaces. 1 space, 2 space, 3 space. So now that we know the frequency of how many times these characters appear, we can calculate how many bits is going to be used within this string. So there's 3 bits to represent A, and A occurs twice, therefore A is going to take up 6 bits. The space uses 3 bits, and there's 3 spaces, therefore there are 9 bits. When we do this for the rest of them, we end up with 58 bits in total. So this whole string can be stored using 58 bits. And you'll notice that P has the lowest amount of bits because it occurs the most. So now that we know how many bits it will take to encode this using Huffman, we need to work out how many it would take using 7-bit ASCII. So if you remember, 7-bit ASCII uses 7 bits. So 7 ones or zeros to represent each character, and here there's 20 characters. So because there's 20 characters, we do 7 bits times 20 characters, and that'll give us 140 bits in total. So if we were to store this string in ASCII, we'd be storing it using 140 bits. In order to calculate how many bits then have been saved by using Huffman instead of ASCII, we can see that we take 140, we minus off the 58 bits, and we've saved a massive 82 bits. So we've been able to reduce this string from 140 bits down to 58, saving us 82 bits. And that's it. You now know how to interpret Huffman trees. You know how to calculate the number of bits required to store a piece of data that's been compressed using Huffman. You know how to calculate the number of bits required to store a piece of data using ASCII. And you know how to calculate the number of bits saved by being able to work out the difference. Next, let's have a look at the worksheet that you're going to be given as part of this lesson. So the sheet that you're being asked to do is the one that's on the screen. As you can see, question 1 says the string truly rural is encoded using Huffman. The Huffman tree below shows how the data is stored. Write the encoding for each character. So you can see here, character A, your job is to figure out how do we get to the letter A. So what path do we need to follow to get to the letter A? So we need to write the Huffman coding here, and we need to write the frequency of the letter in the string here. So if we look, we can see there is 1A, therefore frequency will be 1, and that allows us to do the Huffman coding there. The next question then asks us to work out how many bits it would be in, how many bits the string would take up if we were to store it using 7-bit ASCII. And then we're being asked to work out what it would be like in Huffman. And as you can see here, I've already put the table in for you to help you with that calculation. The next page on question 2, we've got a similar question. Again, this time I have not put the characters in for you, you need to put them in. I've not put the calculation in for you, you need to work the calculation out. And then again here you can see it's a little bit harder because I've not put those calculations in. So the final part of this worksheet then is some interleaved questions. Here we have a decimal number, 111. What's that in binary? What's it in hexadecimal? Here we have the binary number. What's that in decimal? What's that in hexadecimal? And here's the hexadecimal. What's that in binary? What's that in decimal? And you're just going to put your answers in that table. Question 2 talks about an image. We list the file size in bits, file size in bytes. And don't forget, you can use the course website if you need to have a look at that. If you need to go back and find out what the formula is for calculating the file size, by all means please do go and do that. This is not a memory test. I'm not seeing what you can remember from the previous sessions. You can go and research this to help you find out the answers. Same then, we've got capital A is stored in 7-bit ASCII as this. Write down what it will be for the others. And then finally, a sound engineer has a sampling rate of 2000 Hz and a sample resolution of 5 bits. What's the minimum file size of a 6-second recording? And again, give your answer there in bytes, so you need to figure that out. But again, please do go and have a look at the course website on how to do that if you're unsure. If you are sure, I'd recommend to go and double check that you know how to do it. Make sure you get the answers right. Again, the focus here is on you being able to go away and research if you're not 100% confident. And even if you are, it's always good to go and double check. As always, if you have any questions, I'm always available by messaging on Show My Homework or via email. Thank you very much. I look forward to seeing your great work.